Deep beneath the waves, in the intricate labyrinths of coral reefs and rocky seabeds, resides a creature no bigger than your thumb. This unassuming inhabitant of the ocean floor possesses an extraordinary ability, a power so immense it defies belief. With a flick of its specialized claw, it unleashes an invisible weapon, a shockwave that momentarily reaches temperatures hotter than the surface of our sun. This isn't science fiction, it's the reality of the pistol shrimp, a tiny marvel whose secret weapon holds clues to some of the most extreme physics known. Known scientifically as Alpheus, or more commonly as the snapping shrimp, these fascinating crustaceans thrive in tropical and subtropical waters worldwide. They are often found in symbiotic relationships, sharing burrows with gobies, or nesting within sponges and corals. Despite their small stature, they are apex predators within their microhabitat, their entire existence centered around the deployment of their astonishing singular weapon. Understanding their environment helps us appreciate the precision and power behind their remarkable hunting strategy. Unlike other shrimp, the pistol shrimp features one significantly oversized claw, often larger than its entire body. This isn't a pincer for grasping, but a highly specialized instrument of kinetic energy. The fixed finger of this claw has a plunger-like structure, while the opposing dactyl, or movable finger, fits perfectly into a socket. This unique design is critical to its mechanism. It allows the shrimp to snap its claw shut with incredible speed and force, setting the stage for the extreme phenomena that follow. The pistol shrimp primes its weapon by slowly opening its large claw, creating immense tension in a specialized muscle. When triggered, this muscle rapidly contracts, slamming the dactyl into the fixed part of the claw. This motion is astonishingly fast. The movable finger reaches speeds of up to 100 km per hour in just fractions of a millisecond. This isn't just a simple snap, it's an explosive, precisely engineered motion designed to displace water with extreme efficiency and velocity. This rapid closure of the claw doesn't directly create a shockwave. Instead, it generates a high-velocity jet of water. As this water jet accelerates from the claw, the pressure immediately behind it drops dramatically, far below the vapor pressure of water. This sudden pressure differential causes the water to literally rip itself apart, forming a phenomenon known as cavitation. Within milliseconds, a tiny, vacuous bubble of superheated vapor forms in the water, the true engine of the shrimp's power. The cavitation bubble is not just an air pocket, it's primarily filled with water vapor and gases that have diffused into the vacuum. Crucially, it represents a moment of extreme instability. The surrounding water, under much higher pressure, immediately begins to rush in, attempting to fill the void created by the collapsing vapor. This inward rush of water is the driving force behind the subsequent events, concentrating energy into an increasingly smaller volume with astonishing speed. Once formed, the cavitation bubble lasts for only a fraction of a millisecond. It rapidly expands to about a centimeter in diameter, then immediately begins to violently collapse. This implosion isn't gentle. The water rushing in from all directions converges on the bubble's center, creating incredible forces. As the bubble shrinks, the pressure and temperature inside it skyrocket, driven by the kinetic energy of the incoming water being converted into thermal energy. The key to the extreme temperature lies in a process called adiabatic compression. As the bubble rapidly collapses, the water vapor and trapped gases inside it are compressed almost instantaneously. There's no time for heat to escape or enter. All the energy from the implosion is concentrated into the gases within the tiny, shrinking volume. This sudden and extreme compression causes the internal temperature of the bubble to surge dramatically, reaching levels far beyond anything imaginable in normal conditions. Alongside the incredible heat, the collapsing bubble also generates immense pressure. At the point of collapse, pressures can exceed 1,000 atmospheres, that's roughly equivalent to the pressure at the bottom of the deepest ocean trenches, but concentrated in a microscopic space. This extreme pressure is a direct result of the water slamming inward at supersonic speeds, creating a localized force that pulverizes anything caught within its grasp. This sudden pressure wave is the true shockwave felt by prey. As the bubble reaches its absolute minimum size, the incredible compression of gases also generates a fleeting burst of light, a phenomenon known as sonoluminescence. This is light emitted from sound, or more accurately, from the mechanical energy of the bubble's collapse. While the light is too dim and short-lived for the human eye to easily perceive, its presence is a powerful indicator of the extreme conditions, the very high temperatures and pressures, achieved within the collapsing bubble. Now, to the central question, how hot does it get? During the peak of the collapse, the interior of the cavitation bubble can momentarily reach temperatures exceeding 5,000 Kelvin, or about 4,700 degrees Celsius. To put that in perspective, the surface of our Sun averages around 5,778 Kelvin. So, for a fleeting moment, a microscopic pocket of water vapor in the ocean achieves temperatures comparable to, and in some measurements even higher than, the very star that warms our planet. It's an astonishing feat of natural engineering. The final stage of this incredible process is the shockwave itself. When the bubble collapses, it does so asymmetrically, creating a tiny, powerful water jet that travels at hundreds of meters per second. This jet, combined with the sudden release of energy and the immense pressure, generates a shockwave. This shockwave, a burst of acoustic energy, propagates through the water at remarkable speed, stunning or even killing small prey with its concussive force. It's a precisely aimed, devastating blow. For the pistol shrimp, this entire complex physical phenomenon serves a vital purpose: survival. The shockwave is its primary hunting tool. Small fish and other invertebrates caught in the blast radius are instantly stunned, disoriented, or even killed by the force. This allows the shrimp to easily capture and consume its meal. It's a highly efficient, though incredibly violent, method of predation, allowing this small creature to dominate its local food web. Beyond hunting, the pistol shrimp also utilizes its superheated shockwave for defense. Should a larger predator, or even a curious diver, approach too closely, a quick snap of the claw can deliver a startling, disorienting blow. While typically not lethal to larger creatures, the sudden impact and noise are usually enough to deter potential threats. It's a versatile tool that helps the shrimp navigate the dangers of its environment and protect its burrow and symbiotic partners. The pistol shrimp's snap is not just powerful, it's also incredibly loud. The sound generated by the collapsing bubble can reach over 200 decibels, making it one of the loudest biological sounds in the ocean. This extreme noise can interfere with sonar systems and is a significant source of underwater ambient noise in tropical regions. It's a constant reminder of the unseen, powerful forces at play beneath the surface, all originating from a creature barely an inch long. The phenomenon of sonoluminescence, specifically the high temperatures and pressures within collapsing bubbles, has captivated scientists for decades. Researchers have explored whether these conditions could replicate a miniature version of nuclear fusion, much like the processes that power stars. While sustained fusion has yet to be achieved, the pistol shrimp's natural ability continues to inspire research into sonic chemistry and the potential for creating extreme energy conditions on a microscopic scale, offering insights into fundamental physics. The pistol shrimp stands as a remarkable example of nature's ingenious solutions. Its unique claw, a precision instrument of immense power, demonstrates how complex physical principles can be harnessed for survival. The rapid claw closure, the formation of a cavitation bubble, its violent implosion, and the subsequent adiabatic compression combine to create a weapon that momentarily rivals the heat of the sun's surface. It is a testament to the fact that even in the smallest forms of life, extraordinary and profound scientific phenomena can be found.